And now for our last section, 10.3, where we're going to look at the differences not just among two means, but what if we have three or more means that we want to compare? Then we can't use a t-test. We're going to use what's called an F distribution or an Anova test, where Anova stands for analysis of variance. So remember, variance is referring to the variance in the data, the standard deviation squared. So I like how your test refers to your text refers to the F distribution as a new distribution because it was discovered in 1922, which was, here we are recording this in 2020, almost 100 years ago, and yet that's new in the world of statistics. So when we use our F distribution, we're going to have two different degrees of freedom numbers. That's important to understand. So it is always a positively skewed distribution. So if we look at our picture here, we see that it's not a normal bell curve. It's what we call a positively skewed because it's more skewed to the left here. It does approximate zero. It gets very, very close. It's asymptotic, but it never actually approaches, never actually touches zero. So we use this Anova tool, which is a tool available for us in Excel and many other statistical programs, to examine if there is a difference between three or more means under independent sampling. So we're back to using independent sampling. We can't use paired means with Anova. Now we're looking at what we call a one-way Anova test. There is a two-way Anova test that we'll look at in a later chapter. So under one-way Anova assumptions, we are assuming that all of the populations are normally distributed. And of course, if that's not true, then we have to have sample sizes of at least 30. We are assuming that the population standard deviations are unknown but equal. Okay, so again, if we don't think the population standard deviations are equal, we can't use Anova. And then again, the samples are all selected independently. So our test is that the mean of 1 is equal to the mean of 2 is equal to the mean of 3 is equal to the mean of 4, or however many. We use C to denote how many different samples we have. So in the example that we're going to look at the end of the video, we have 3 samples, so we're going to have C would be equal to 3. Now, the alternative is that not all the population means are equal. Now, that doesn't mean that none of them are equal. It doesn't mean that maybe, for example, mean 2 and mean 3 aren't equal. It just means that all 3 or 4 or 5 or however many we have are not all equal. So if just one is different, then we would reject the null hypothesis. So I want to make that very, very clear. If we reject the null hypothesis, we're not saying that all 3 or 4 or 5 or however many means are different, just that all 3 aren't the same. Okay, and we'll look at that in our example data in a moment. And so if we have one sample mean, and then we have 2, and then we have 3, and here we have 4 sample means, notice how we can look together. We're really looking at the variance in the different sample means. So if the sample means are all relatively close together, then it looks like this diagram on the left. Where it represents more, it's approaching a bell curve. But if the sample means are all different, very different, then we look like this diagram on the right. So this would lead us to reject the null hypothesis. Now notice though that, for example, the mean of 3, the green loop there, and the mean of 4, the purple loop there, are very close together. Those may not be different, but they are different from 1 and 2. So we would still reject the null hypothesis, even though some of the means may still be equal, or at least not statistically significantly different. So again, one-way Anova is looking at difference between the population means, and they use that using the population variance, so that's sigma there. So there's 2 different kinds of variances that we have, which is why we have 2 degrees of freedom here. We have the variance between the sample means, so that's called between treatments variance. And then we have the variances within each sample data. So that's within treatment variance. So if all of these are close together, then we do not reject the null. But if they are significantly different, we will reject the null. So again, here's our formula for our F distribution, where MSTR is the between treatment variance and MSE is the within treatment variance. Okay, and we'll see that in our Excel output. Now, when we get our data table from Excel, it looks something like this, where we have the between group, what we call the sum of squares, and then we have the within group sum of squares, and that gives us the sum of squares total. That's not really what we're really interested here, but it is interesting. So then we have our F statistic, that's our test statistic, and then we have our p-value, which is what we're primarily concerned with. So when we look in Excel, we're going to still be using that data analysis section, and we're going to look at that here in just a moment. And then we're going to choose data analysis, Anova single factor. As I said, we'll use the other one later. Notice there's only one input range. So we're going to put all of the data in at one time. Then we'll choose whether the data is grouped in rows or columns, whether we have labels in the first row, what is our significance level, and then how we want the output. So let's jump over to Excel now. We're going to be in the exam scores worksheet of your Chapter 10 workbook, and let's practice this. So here we have some data from a particular professor, not me, but this is from a particular professor who is examining the test scores in her section. So she is teaching 3 sections of a course, and she wants to know if the test scores are significantly different between the sections. And there's a lot of different scenarios, maybe it's that night students are doing better or night students are doing worse. Maybe she's testing whether her 8 o'clock section is performing significantly, worse, or maybe she thinks that they're performing significantly worse, or maybe she's worried about the test leaking. So the first section of students take the test, and then they go tell their friends in the second section, and then they tell their friends in the third section. And so by the time we get to the third section, those students already know what's going to be on it. I don't know what the scenario is, but we have those test grades. Now notice that we don't have 30 grades, so we're assuming again that this is normally distributed data, which is a pretty fair assumption with respect to test scores. So we're going to go up here we're in our data tab. We're going to go to data analysis. Data analysis. We're going to choose Anova single factor. Now again, my input range, I'm going to select all of my data, so A1 through C11. My data is grouped by columns. I do have labels in the first row. And let's just go with a 95% confidence interval. Oh, let's do something different. Let's maybe do a 99% confidence level. So maybe 0.01. Really doesn't matter. It doesn't actually affect the p-value. And then for my output range, I want to put this in E1. I'm going to select OK. Now here we get all of the data, so we can see that the average in section 1 is a 72.8, the average in section 2 is a 78.7, and then the average in section 3 is a 69.4. So certainly it looks like there's a lot of variation in the test score. So I can understand why this instructor might think, I wonder why is it that section 2 is, performing almost 10 points higher than section 3. So notice that we have our variance between groups and as well as our variance within groups. We have our F statistic here. We could look this up in the table if we wanted to, but really what we're interested in is this p-value here. And this p-value is really, again, what we want. Now, the p-value is 0.14, so we could not reject the null hypothesis even at the 10% significance level, right? Because it is so high. So even though it looks like there's a fairly significant amount of difference in the averages, according to this, it's not significant even with a 10% significance level. So we cannot reject the null hypothesis that one section is doing better than the other, or rather that the sections are not all performing the same. So we can't reject the null hypothesis that the average between the sections is significantly different. So I wanted to point that out. Now, one other thing that I want to point out real quickly before I let you go is what's called the grand mean. So the grand mean it's denoted as X bar bar. So think of the X with 2 bars above it instead of just 1 bar for the mean. So the grand mean is calculated based on the weighted sum of all of the squared differences, okay? So we're going to sum all of the observations. So here they've been summed for each one of our sections. So we would sum these. So we could say this section 1 sum plus section 2 sum plus section 3 sum. And then we divide it by the total number of observations. So here we have 10 observations in each group. So I'm just going to add those in my head and say 30, but certainly we could say F5 plus F6 plus F7. So, I didn't put my parentheses in correctly. I love how Excel tells me that. So here my grand mean, like the overall average of averages, if you will, is a 73.63. So the overall course average is, or test average, we should say, is 73.6, even though the average in the various sections range from a 69.4 to a 78.7.